So if you've ever learned anything about matrices, you might recall that you're only allowed to multiply two matrices if their sizes match in some certain way. So I won't recall exactly what that way is here. But after learning that, you might ask yourself, is there some sort of more general way to multiply matrices where I could multiply matrices of two different sizes, or of any size, I should say? And in fact, there is a way. Well, I think there's probably several ways, but the way that we're going to explore today is called the Kronecker product. So let's first define it, and then we'll look at an example, and then we'll talk about some properties or one certain property of the Kronecker product and talk about why it's an interesting object. So let's say that A and B are matrices of any size. Then A circle times B, so it looks like A tensor B, and we'll see kind of why that notation is adopted, is going to be this somewhat larger matrix. And so this is given by block matrices. So here we have the A11 matrix times the entire matrix B. So that's like a scalar multiple of the entire matrix B. Then the next term will be the A12 entry of A times the entire matrix B. All the way up here is the A1 entry of A times the matrix B. And then we fill out the rest of this product similarly. So way down here, we have the AMN entry of A times the matrix B. Okay, so let's look at an example of this Kronecker product to get an idea for how this goes. So let's say we take the matrices 1, 3, 2, -1, and we do the Kronecker product with 2, 1, 5, 4. So something like that. So I'm going to stay with 2 by 2 matrices just because that keeps the calculation like fairly nice. Okay, so let's work through it. So this is going to end up being a 4 by 4 matrix. And so this upper entry right here will be 1 times the matrix 2, 1, 5, 4. So that would be related to this block matrix right here. And then next we'll have 3 times the matrix 2, 1, 5, 4 in this entry. Here we'll have 2 times the matrix 2, 1, 5, 4. And then down here we'll have -1 times the matrix 2, 1, 5, 4. So something like that. But now we can just expand this thing out without too much difficulty. So we'll have 2, 1, 6, 3 in this first row, and then 5, 4, 15, 12 in this second row. Next we'll have 4, 2, -2, -1 in this third row, and then finally 10, 8, -5, -4 in this fourth row. So that would be our final answer here. So that is the Kronecker product of these two 2 by 2 matrices. Okay, so next up we'll prove a certain result related to this Kronecker product, and we'll also maybe say why this might be an important object to look at. Okay, so the result that we'll prove is that if A is an M by M matrix and B is an N by N matrix, then the determinant of the Kronecker product of A and B is the nth power of the determinant of A times the nth power of the determinant of B. So I think this is a pretty nice result. And then this fact, which we won't prove, but I think gives a lot of motivation for this definition of the Kronecker product, goes like this. So if we take the Kronecker product of a matrix A and a matrix B, and do matrix vector multiplication with the tensor product of two vectors V and W, living in a tensor product vector space where we choose kind of an obvious basis, then that'll be the same thing as the matrix vector product of A with V, the matrix vector product of B with W, and then we take the tensor product between them. So what this is saying down here is that this Kronecker product up here is the matrix version of the tensor product of two linear transformations. So maybe post in the comments if you'd like to see a whole video about the tensor product of linear transformations. I think that might be fun to make. Okay, so now let's look at this first fact, and we're gonna like sketch out a proof. We're not gonna work out all the details because it gets a little bit tricky with all the indices. We're gonna look at a 2x2 case to motivate a certain result and then prove it from there. And I think this 2x2 case gives us some motivation for how this works anyway. Okay, so let's look at the following Kronecker product. A, B, C, D, Kronecker product with the identity matrix. So 1, 0, 0, 1. Okay, great. So now, based off of our example before, we know that this is equal to A, 0, 0, A. That's our top left block. And then we have B, 0, 0, B, C, 0, 0, C, and D, 0, 0, D. Great. Now we'd like to talk about the determinant of that, but let's recall that we can perform row and column operations. And if we're careful, we can note the changes that it makes to the determinant and then use that to maybe find the determinant of a simpler matrix. So let's do that. So let's do the column operation, which is C2 is replacing C3, or they're swapped. So in other words, the second and the third column are swapped. So let's see what that'll leave us with. We'll have A, B, and then 0, 0, C, D, and then 0, 0. So those will be our first two columns. And then our third column will be 0, A, 0, C, like that. And then our last column is unchanged, so 0B, 0D. So we have something like this. And then let's recall that when we take the determinant of our resulting matrix, we get the negative determinant of the original matrix. That's what that column operation does. Okay, so next up what we'll do is we'll do a row operation. So the row operation I'll do is replace row 2 and row 3, or swap row 2 and row 3. So this will have the effect of multiplying the determinant by another -1, which means the determinant will end up being multiplied by -1 squared, or in other words, the number 1. Okay, so let's see. Row 1 and row 4 do not change, so let's maybe copy those. And then we're swapping row 2 and row 3. So that gives me C, D, 0, 0, and then 0, 0, A, B. So something like this. But now let's look carefully at that and notice that we've built a block matrix where we have all zeros, or a zero matrix on the off diagonal. And then we have our original matrix. That's the left-hand term of our Kronecker product on the diagonal. So that means that when we take this determinant, we'll have the determinant of this upper 2x2 times this determinant of this lower 2x2, but those are the same. So let's do that. So let's say this squiggly line is to take the determinant, and we'll see that this is AD minus BC quantity squared. So something like that. But notice that definitely fits our formula up here. That's equal to the determinant of A, B, C, D to the second power. This is a 2x2 matrix, times the determinant of 1, which is the determinant of this, to the second power, because this is a 2x2 matrix. So that fits our rule over here. But what we'd really like to do is look at the general case. And like I said, the general case has essentially the same proof with row and column operations. You just have to be careful about keeping everything straight. But what we have is that a Kronecker product with the n by n identity matrix is row and column equivalent to a block matrix with a bunch of A's on the diagonal and then zeros on the off diagonal. So that means when we take the determinant of this type of object, we get the determinant of our block matrix A to the n power, because we have this right here. And that's what we want to keep in mind. And then similarly, if we take IM, so the m by m identity matrix, and we do the Kronecker product with B, that's not just row and column equivalent to this type of block matrix. It's actually straight up equal to this type of block matrix. So that's cool. But then that, when we take the determinant, is kind of exactly what we want, the determinant of b to the m. So now let's use these two general facts to maybe prove the rest of our claim over here. Okay, so on the last board, we derived these following identities, and we didn't quite derive them as much as we just looked at evidence for why they should be true. But to be honest, the proofs are essentially the same. You just have to be careful with all of your indices. And now from these two red underlined identities, we're ready to finish this thing off. So let's take our determinant of our Kronecker product of A and B, and let's actually factor this Kronecker product of A and B as follows. So this is going to be equal to A Kronecker product with the n by n identity matrix, and then the normal matrix product with the m by m identity matrix Kronecker product with B. So something like that. And we definitely haven't proven this, but that being said, based off this definition over here, I think this would be like a nice homework problem to work through, just that this factorization holds. Or really, it's probably easier to prove in the reverse direction. So it's easier to prove that if you take the normal matrix product of those two matrices, then you get exactly what you want. But now we know the determinant factors over matrix products, and this is a normal matrix product here. So that'll give us the determinant of the Kronecker product of A with IN times the determinant of IM Kronecker producted with B, but then we're done. So this is the determinant of A to the n power times the determinant of B to the m power as we desired. Okay, so like I said, if you'd like to see a follow-up video about the Kronecker product as a matrix version of the tensor product of linear transformations, maybe post in the comments. And also, I've done some other videos on tensor products, and there should be one on the screen right now if you'd like to check it out. And that's a good place to stop.